In lesson 13, we're going to start looking at some more laws of logarithms. We've already seen a few. In particular, today we're looking at the product law and the quotient law of logarithms. Remember, logarithms are just another way of thinking about exponential relationships. So we already know that there's some power laws. For example, we know that if we multiply two powers with the same base together, then we end up adding the exponents. There's a parallel law for logarithms, but because, again, they're just rewritten in a different form, they're going to look a little bit different. So the product law of logarithms says that if we have let's not make that a 2, let's make that an a, just some base, and we take the log of some argument, where two things are multiplied together, we'll call them x and y, that's equivalent to the log of x plus the log of y. And again, the base is just a. But you'll notice that on the exponential side, we multiplied, and when we multiplied them, the exponents were related by addition. Likewise, we're multiplying, and the logs are related by addition on this side. So there's some parallel mathematical processes going on. And for exponent laws, we could divide, and if we divide by two powers with the same base, we end up subtracting the exponents. So again, if we're going to divide logarithms, then we're going to end up subtracting the logarithms. Like that. And just like we have a power of a power for exponent laws, where we raise one power to another exponent, we multiply the exponents together, we've seen that there's a power law of logarithms, but in this case what we do is we take the exponent and we bring it down as a multiplication out front. So again, there's parallel things going on here. And finally, we have what we'll call the same base formula. If we have a logarithm to some base, and then our argument also has a power with that base in it, then what happens is that, remember what we're saying is, what exponent do I have to put on a that's going to equal a to the x? Well, of course, the answer is x. So it's like those two bases cancel each other out, just leaving the x. Or if I do, to turn that around a bit, if I have an exponent, a power that's raised to the exponent of a logarithm, then again, we got these two bases canceling each other out, the a base for the logarithm with the a base of the power, and again, we're just left with x. So it's like we're combining the inverses together, where all we're left with is x. Now, just a quick proof, I'll do it quickly anyway to show where this comes from. If I want to show where the product law of logarithms comes from, I want to prove that log of some base xy is equal to the log of that same base a of x plus the log of y. So to do this one, we're going to do a little substitution. We're going to let some random variable, in this case, well, let's make it m, equal log base a of x. So we're going to take this, in other words, and just let m equal that. And we're going to let n equal log of y. So we're going to take this part here, and we're going to do this substitution here. So then we can rearrange this and put it in exponential form, because we've seen that putting things from one form to another can often be helpful. So if I want to just rearrange this formula, m equals log base a of x, in exponential form, I'd write it as a to the m equals x. Likewise for the y, I could write this as a to the n equals y. And then I can substitute this back into the left side of the equation. So if I want to work on the left side of the original equation, that would be this, right? That's the left side of the original equation I'm trying to prove. Then I'll start with that, but I could swap out x and y with a to the m and a to the n times a to the n from above. That's this and this just being substituted in here in place of x and y. We've seen just above the same base formula, if we take the log of something, we got this base a, and then we got the same base. Let's simplify it a bit more before we go to the final step. Remember, we can do a to the m times a to the n equals a to the m plus n. But now let's take a look. We got this base a, we got this other base a. In essence, everything cancels out, and all we're left with is m plus n. But m was equal to log of x, and n was equal to log of y. So that's going to equal log base ax plus log base ay, which is the right side of the equation that we started with. So we've just done our proof. So I'm going to leave the quotient law for you to take a look at on your own, but you could do it the exact same way, even use the exact same substitutions as I did above, but instead of multiplying, you can try subtracting and see what happens. So if we take it that these laws of logarithms are true, then we can use them to help us solve some different problems. And we can combine that with what we already know, which is that we can switch back and forth between exponential logarithmic forms when that's handy. We can use the power law of logarithms that we already know. So we've developed quite a few tools now to help us simplify things. So this first one, right is a single logarithm. All right. So what we notice is these all have the same base. So we can use some of these laws. So if I add, I know I'm going to multiply. So let's just look at that part first. I could rewrite these first two terms as log base 5 of 6 times 8. That dot just means times. And remember, the subtraction means I'm just going to divide. So I already know that 6 times 8 is 48. Let's actually just write that out. Don't need to have those brackets there, but they're just left over from when I did have them. I didn't erase them. So anyway, whether I put the brackets on 48 or not, I can also then subtract by dividing. So I could do 48 divided by 16. So these laws work in both directions, and that's again because these guys have the same base here. So 48 divided by 16 becomes 3. So it's log base 5 of 3, which I would need to, if I wanted to go any further, that's going to be a decimal answer. I could do that in my calculator using the change of base formula, but that wasn't what we were asked to do. We were just asked to write as a single logarithm in this case. In the next one, again, these are all common logs, right? They all have no base specified, so we assume that they have a base of 10. So we can combine them. We are going to add, and subtract. So let's do it all at once in this case. So it's log base 10 assumed to be the case. So we're going to multiply the x times the y times the 3x, because those are all added together, times y times 3x. And we're going to divide that by the y here, because that one was subtract. So again, highlighting just meant to show where things are coming from and to highlight various things as we go along. Now, as we can see already, we've got a y over a y. Those can cancel out. And what I'm left with is log of x times 3x, which is just 3x squared when I multiply that out. And I can't go any farther, so that would be my simplification for this one. So we can bring things together and simplify them. What we can also do is we can use it to evaluate, use these rules to help us evaluate things. So we look at this first one, part A, and it might look a little bit complicated, maybe it doesn't, but we can make it less complicated because we can combine them together. They have the same base, they both have the base 8, and it's adding, so we can multiply these parts, and we've got log base 8 of 4 times 16. And 4 times 16 is just 64. We could go to our calculator, but this is one we should be able to figure out for ourselves, because what we're asking is what exponent do I need to put on 8 to equal 64? And hopefully it's obvious that it's 2. 8 squared equals 64, so that would be our answer. But if you don't see it, confirm it on your calculator. You'll get the same answer. All right, the next one, log base 3 of 405 minus log base 3 of 5. Again, we can combine it, this time as a division since we're starting out with a subtraction. And 405 divided by 5 equals 81. So again, the question becomes, what exponent do I need to put on a base of 3 to equal 81? And hopefully you know this one. If you don't, go to the calculator, but 3 times 3 is 9, times 3 again is 27, times 3 one more time equals 81. So 3 to the exponent 4 equals 81. That's our answer. This one's different because now we've got some numbers in front of the logarithm. So we're going to have to go back to the power of logarithms law that we've used before to help us out. So we remember we can take this 2 and we can bring it up as an exponent on the 5. And we can take this 1/2 and bring it up as an exponent on the 16. Remember what fraction exponents mean? It means just take the square root. So 16 to the 1/2 equals 4. So I'm going to work backwards on this one. 16 to the 1/2 equals 4. So I can simplify that a bit. And 5 squared is just 25. So now we're in a position where we can then use our multiplication of logarithms law. And so 25 times 4 equals 100. And since this is a common log, it's got a base 10. So we ask, what exponent do we put on 10 to equal 100? The answer is 2. So no calculator is required to simplify that complicated looking logarithm, as long as we know our laws. Now we've got a few more difficult looking ones. They're just bringing in, really doing the same thing, just bringing in some extra difficulty, just some reminders of what exponents need to look like and how to work with them. So again, we just talked about square roots being, they can be represented as fractions. So I could rewrite this as x to the 1/2 over x squared. And then going back to what we already know about exponent laws, we know that we can subtract these exponents. So I could do 1/2 minus 2. And so that would be the equivalent as x to the negative 1.5 or 3 over 2. Let's show this one. I feel like I might lose somebody if I don't show this one. So remember, it's just going to be the same as x to the 1/2 minus 2. That's using exponent laws. 1/2 minus 2 is equal to 3/2. Well, negative 3/2. So that's where I was coming from for the previous line. So that is pretty much all we can do with this one. We can't simplify it anymore. I could write it without the negative exponent because sometimes that's considered more simplified. So I could write that as 1 over 3 x to the 3/2. I do need to put a restriction in this case, x has to be greater than 0. And the reason why x has to be greater than 0 goes back to this part here. We can't take the square root of a negative number. So there's different reasons that we put restrictions on things. Sometimes it's if we have division by 0, but sometimes it's, well, in this case, it's the fact that we can't take the square root of a negative number, so x has to be greater than or equal to 0. It would just be greater than 0, but it can't equal 0 either because of the denominator here. If x actually equals 0, then we're dividing by 0. So put those two things together and it has to be greater than 0. Combining the next one, we can rewrite, let's just rewrite as exponents first. So this can be rewritten as log x to the, well, this can be 1/2. Let's show it. Let's show every little bit. So it's going to be 1/2, whoops, change my pen, 1/2, and we're still raising it to the exponent 3. Nothing to do on this one. And this one we're going to write again as 1/2, log x to the 1/2. So this 1/2 to the 3, we know we multiply, so it just becomes log x to the 3/2. And then we're going to add, and we're going to subtract, which we know in the next step is going to become multiply and divide. We can combine these all together to a single logarithm, so it's going to be log. And so the multiply part is going to be x to the 3/2 times x squared over x to the 1/2. So we combine those 3 logs into 1. And again, if we add the exponents in the numerator together, we get, let's just change this 2 change this 2 to a common denominator of 4 over 2. Because now all our exponents will have a common denominator. So we're going to add 3/2 and 4/2, we get 7/2. We're going to subtract 1/2, we get 6/2. So that ends up being x to the 3. And again, let's think, do we have any restrictions? Well, again, we've got square roots going on. So in this case, x has to be greater than or equal to 0. And this time x can equal 0, that would be okay. But that's strictly from this one. Well, it could be this one over here as well. No, actually it doesn't, because we can take the, well, yeah, I guess, well, I can say we can take the cube root of a negative number, but that's not what we're doing. Yeah, same problem here. We can't let x be less than 0. Can't take the square root of a negative number. But we can take the square root of 0, so that is okay. Last one, okay, we've got binomials. What do we do with this? Well, we just approach it using our laws of logarithms and hope everything will work out. That's all we can do. So if we see something we're not used to, we got a subtraction here, so we can think, okay, let's try dividing and see what happens. So now I've got 2x minus 2 divided by x squared minus 1. And I can definitely simplify this. I can factor the top and the bottom. Let's see what happens. And then when I do, this x minus 1 cancels out. And so I'm left with log of 2 over x plus 1. Again, we're going to have some restrictions. In this case, x is going to have to be greater than 1. And the reason why is because if x is anything less than 1, I'm going to be taking the logarithm of a negative number in this case. And we can't take logs of negative numbers, so that would give us an error. And also, even in this case as well, if x is anything less than 1, when I square it, I'm going to have a number smaller than 1 in the brackets. Sorry, smaller than 0 in the brackets, and I can't take the log of that. So in either one of these cases, both of these brackets are causing the same restriction. X has to be greater than 1. So that's a selection of some of the different ways that we can combine these rules to simplify things and sometimes to evaluate things as well. But we can put them together in whatever order is necessary to serve our purposes. Sometimes it takes a little leap of faith, though. You may not see the end when you start out, but just start applying the laws and see what happens. So there's lots of practice as far as that goes.